About Ampere's law, or introduce Ampere's law. Ampere. So this is sort of the same idea as we had with Gauss's law when we were talking about the electric field. We have this finite amount of charge inside a closed surface, and by doing an integral over the surface, we could calculate the electric field. In this case, we're going to have a current in a loop, and by calculating the magnetic field around the loop, or adding up the magnetic field around the loop, and knowing the current inside the loop, we'll be able to calculate the magnetic field. And like Gauss's law, Ampere's law is always true, but you need a nice structure of some kind, a nice geometry to actually calculate the field using Ampere's law. So here's the setup. Current, just like always. There's a current flowing into the board, a nice straight wire. We know from what we did previously, there are magnetic field lines that wrap around the wire. I put my thumb of my right hand in the direction of current flow, and the field lines go around this way in the direction of my fingers. So here are those field lines. They're nice concentric circles. Field is like this. That's B. Okay? So I'm going to make a loop at some radius r. It's arbitrary. So here's the radius r, and I'm going to go around the loop with those little displacement vectors ds that you've seen before. ds and ds. Okay? It's a terrible drawing, but take the integral around the closed loop of b dot ds. So marching around the loop, and I'm multiplying the field times that little length and adding it all up. Let's take care of the dot product. The angle between B and ds, the way I've set this up, is 0. It's a dot product. The cosine of 0 is 1. So this just becomes the closed integral of B ds. Get rid of the vectors. All right. For a given radius r, we know that for a straight wire, the magnetic field is a constant at that radius. The magnetic field is not changing as I go around this loop that I've drawn. So this can come out of the integral. I'll go down here. So this equals b times the integral of ds around the closed loop. What's the integral of ds around that loop of radius r? What's the length? Let's see, if I have a little bug and it's crawling around here at this distance r, and it's adding up how far it goes around the loop. 2 pi r. This is equal to 2 pi r, the circumference of the loop. So this is equal to b times 2 pi r. But we know what b is for a long straight wire at a distance r from the center of the wire, and that is b is equal to mu naught I over 2 pi r. I'm using r this time, so Okay. Replace this, and it's like magic. You get mu naught I over 2 pi r times 2 pi r. And this is equal to mu naught I. Ampere's law says the closed integral of b dot ds is equal to mu naught I enclosed. Okay? Just like we had with Gauss's law, you had the closed surface integral of E dot dA is equal to Q enclosed over epsilon naught. This is the same form. Okay. I enclosed means you only count the current that's in your loop, and it's independent of the shape of the loop. Okay? But you know, you need a nice geometry to be able to calculate B. Give you a couple of quick things. Let's say that this is the current, this is current going into the board. This is the same current going out of the board. Okay. This would be, depending on what we call the positive direction, this would be a positive current, this would be a negative current. If I enclose it in a loop like this, okay, Ampere's law will work. It's ugly. If I actually want to calculate it along this path, it's going to be ugly. I got to take ds and know the field direction. But Ampere's law guarantees if you go around that closed loop, you're going to get 0. I enclosed is 0. You have current going into the board, you have current coming out of the board, and they're equal. Okay? The wires that Xfinity and others bring into your home, and I'm not talking about fiber, but like the black coaxial cable, you know what I'm talking about? Like you screw it in, it's got that copper, center copper conductor. It's called coax because you have that center conductor, and then out here is a mesh surrounding the cable. Okay? There's a mesh. Coaxial cable is nice because if you have, let me change that around since I made these X's. If you have current flowing out of the board in this direction or current in this direction, that shield or that outer conductor, the current's all flowing in that direction. And Ampere's law says if you enclose it in a loop, okay, like this, and you calculate the B dot ds, you're going to get 0. But because of symmetry, this being coaxial like this, out here, B is actually equal to 0. That's the beauty of coax. It's quiet. If you have current flowing in it, you don't get an associated magnetic field outside the coaxial cable. You don't get noise. It does other things too. It's a shield. This is usually grounded. Okay? But yeah, that's one of the reasons it's coax. Noise. Okay? So I want to look at the magnetic field of a solenoid. And we're going to calculate that magnetic field using Ampere's law. A solenoid, well, what is a solenoid? Anybody happen to know? Solenoid. S-O-L-E-N-O-I-D. A solenoid. Solenoid's a big coil of wire. It just so happens I have one. Okay. So this is a cylinder with a bunch of turns of wire around it. Very close together. Okay, tightly wound, as they say. And the length is much longer than the diameter. That's what makes it a solenoid. You can have a coil like we had in lab, where we had that big fat coil, okay? That's kind of like a solenoid. It's a coil of wire, but the length of that thing is about the same as its diameter. For something to truly be a solenoid, it needs to be much, much longer than it is wide, or, the diameter. You get a nice uniform magnetic field inside the solenoid. So you put current through the coil, and you're producing a magnetic field inside the solenoid. And outside the solenoid, the field lines are always closed loops, but outside the field is pretty negligible if you measure it. Okay, you get these big, long, spread out field lines, and it's pretty negligible, okay? Compared to the field inside. So I'm going to draw the solenoid cut along the axis, not the cross section, but cut along the axis. So here it is, like this, and this. I'm going to get rid of that. So I sliced it, and there's all those little wires. And here they are. I'm making them really big, but okay. You can look this up. There are some very nice drawings people have done on the internet and so forth. So the current's going around this way. These are all the little loops, tightly wound. So I'll say the current is into the board here. Okay. And it's coming out of the board here. It's all the way. I'm just drawing a little section, but these turns are all the way up and down. All right. Inside the solenoid, you get this nice uniform field. Okay, I'm representing it with one vector. Outside B, we're just going to say B is equal to 0. Negligible, or it's really, really small compared to this. Here's my Amperian loop. Like a Gaussian surface, you have an Amperian loop. That's it. It's a little rectangle. I'll call this point A, this is B, this is C, this is D. And I'm going to go around the loop clockwise. I know this is all contrived, but it works out pretty sweet, okay? You could choose any loop, but this loop makes it easy to calculate. That's my closed loop. So to do Ampere's law, I've got to take the closed loop integral, which is the integral from A to B of B dot ds, plus the integral from B to C of B dot ds, plus the integral from C to D of B dot ds, plus, last one, the integral from D back to A of B dot ds, and all of that equals mu naught I enclosed. Okay. Let's look at this integral from A to B. from A to B, okay, ds, I'm going this way, ds and B are in the same direction. The angle between them would be 0. Cosine 0 is 1. So this just becomes equal to the integral from A to B. B is a constant inside of ds, okay? I'm going to call that little length S, why not? So this is equal to BS. You knew that all along. Okay. I like that result. Okay. That's just that little length here times the field, B. Let's look at this integral from B to C. Well, inside the solenoid, the angle between B and ds will be 90. No contribution. Cosine of 90 is 0. Then you have the transition here. We're going to say that at this point, field, no field out here, so this is 0. C to D. C to D, B out here is negligible. It's equal to 0. This is 0. From D to A, same argument as B to C. You get 0. So in the end, you have BS is equal to mu naught I enclosed. How much current is enclosed in my loop? Well, here's the way you can handle that. I've got, let's say this thing has 1,000 turns. I've got some number of turns in the loop depending on this length. So if I make n, little n is equal to the number of turns per unit length, okay? Then if I multiply that number of turns per unit length times the length times I, each turn has I, right? Maybe I didn't write that down, should have. Each little turn has, they all have the same current flowing through them, okay? Then I enclosed is equal to NSI. That's the turns per unit length, that's the length, and that's the current in the turn. So replacing that here, I get BS is equal to mu naught NIS. S is cancel, and you get B of the solenoid is equal to mu naught NI. That's it. Where little n is the number of turns per unit length. This is a pretty good, this is assuming that you have a long tube and it's really small, okay? But you can take I've got a solenoid over there in the lab that I made out of a paper towel tube, and you can actually measure it. You can measure the field inside, and it's really close to this, okay? This would not work for that big fat coil that we have. On that coil, it's a different story. It's not a solenoid. Okay. So for a solenoid, here's a solenoid, here's a tube of length L. and radius r. For a solenoid, you need L to be much, much greater than R, okay? That's what I'm saying. Then this works well. Students always ask, well, how much is much, much greater? Okay, order of magnitude, 10 times. If you have a 5 centimeter radius, 50 centimeter length, something like that, okay? All right, let's calculate the magnetic field for some solenoid like the one I've got over there in the lab. I'm going to let capital N, which let me write it out, number of turns I think the one I have over there has about 450 turns. Okay. Length is equal to, let's say 20 centimeters. That's long. Lots of turns. No, that's good enough. Current, it's a really fine wire. I'll let the current equal 0.25 amps, 250 milliamps. So a fourth of an amp. So what kind of field? I'm calculating B sol. That should be on your equation sheet. So B is equal to mu naught 4 pi times 10 to the negative 7 Tesla meter per amp times number of turns per unit length. So that's 450 divided by 0.20 meters. And then the current is 0.25 amps. Would someone be so kind as to calculate this for me? .25.
706 millitesla? Or, yeah. I got 0.3000706.
What'd you get? That sounds big to me. Well, no, that sounds really, really small.
What'd you get? I got a really small number.
0.007.
0.00. I must be off by order of magnitude. I have 3 zeros.
Did you convert to meters?
Yeah, I converted to meters.
20 centimeters.
0.3.
I got 0.007.
Okay. What'd you get?
7.069 times 10 to the negative 4.
Yes. That sounds better. 7.1 times 10 to the negative 4 Tesla. Is that what you got?
Yeah.
I was here in 0.007.
Yeah, I got that.
I got
To the
another
third,
zero.
negative 2.
I had another zero.
I got that.
You had another 0. Okay.
Negative 4.
Yeah. Okay. 7.1 Gauss. That's 7 times the Earth's field, which the Earth's field is really tiny. So, yeah.
Why on our equation sheet does it say B sol is equal to mu naught N over L times I?
Is it a capital N?
Yeah.
Yeah, that's the number of turns per unit length. I'm calling little n here.
Okay.
Little n is equal to big N, which is the number of turns divided by the length. Okay. All right. This is the way you make those uniform fields that I've been drawing. Okay, you have a solenoid, You have a nice uniform field and you have a little hole in it and shoot a particle into it and watch the particle spin. Okay? All right. Any questions on this? Okay, that's it. That's it for all the stuff we're going to do in these 2 chapters. So I got to put some homework together for this. Then we're going to start talking about induction.
Can you go over the right-hand rule one more time?
Which one?
For like,
That one?
yeah, the favorite one, like the.
Sure. Okay, someone has produced a uniform magnetic field in a solenoid. And here it is. It's coming out of the board. Okay. So the little dots, I mean, you know, I could draw a circle, but I'm just going to make them dots. Here's B. All right. Here comes an electron. E negative at velocity V moving into that field. So, you know, this is a typical first question test problem. Okay. Which way is the electron going to circulate? Is it going to be clockwise or counterclockwise? Well, this is V. This is the velocity vector. This is B, the magnetic field vector. Middle finger is magnetic. Index finger is point in the direction of the velocity. This gives you the direction of the force. But, okay, so I've got, that's the direction of the magnetic field, that's V, but it's a negative particle, so I have to flip the force direction. So this particle is going to go around counterclockwise. Boop. Is that good, Owen?
Yeah, that's good.
Okay. Yeah, you got to move your hand around. And you have to flip, because with cross products, well, it's not just because it's a cross product. If you have QV cross B, okay, that's equal to, as far as magnitude, that's equal to, well, let's not talk about magnitude. If this is negative, you know, this is a constant multiplying this thing. If this is negative, then it's just flipping that direction. It's making that vector negative. Okay. That's the reason. These cross products, you know, any cross product that you meet, A cross B is equal to C. This is your index, middle, thumb. Okay. Cross products do not commute. You know, we're used to things commuting, like 5 times 7 is equal to 7 times 5. Not so with cross products. They anti-commute. So B cross A is equal to minus C. Okay. The anti-commute. And this would work, right? This would still be index, middle, thumb. You've swapped your index and thumb direct. You've swapped your index and middle direction. Okay. The cross product, remember how when I told you about I don't want to get way deep into these cross products. Maybe we should, but remember when we had the dot product, you had A, B, and this is the angle theta. Then A dot B was a scalar, call it C. That was the projection of A onto B, and you multiply it together. Okay? Or it's the projection of B onto A. Okay? Doesn't really matter. For the cross product, if you have two vectors A and B, here's A, here's B. Okay. So the way I've drawn them, A cross B, will be like that. Let me move this over here. Okay. These form a parallelogram, like this. Okay. C, the resultant, would be here. Okay. This, the area of this parallelogram, is the length of C for the cross product, and this vector C is perpendicular to the plane formed by A and B, or normal to the plane. That's how you get the cross product. It's the area of the parallelogram formed by A and B. That's why it's sine theta. If the angle between the two is 0, this has 0 area. Okay, if the angle between the two is 90, then it's a rectangle. It's just A times B. Sine of 90 is 1. Okay, so that's the geometric idea of this vector formed by the cross product. Okay. Okay. I keep going. In component form, here's a nice little trick. Okay, if you go around this way, this is clockwise. I hat cross j hat is k hat cross I hat is j hat. K hat cross I hat is j hat. What did I say? Anyway, I'm messing up. I hat cross j hat is k hat. J hat cross k hat is I hat. Okay. Yes, thank you. I'm going too fast. Okay, if you go the opposite direction, counterclockwise, I hat cross k hat is negative j hat. K hat cross j hat is negative I hat. Last one, right? J hat cross I hat is negative k hat. Okay? So if you're crossing two vectors in component form, there's a lot of ways to do this. Let A equal AX I hat plus AY J hat plus AZ K hat. Let B equal BX I hat plus BY J hat plus BZ K hat. Okay. If you have A cross B, you can multiply these all out. It gets really ugly. Okay. And when I say multiply, you can cross the two vectors and do just like you would with any trinomial. If you were multiplying it, multiply this through the first, multiply this through, multiply this through, taking all those cross products in the correct order. Okay. But you can also make this little device, I hat, j hat, k hat, ax, ay, az, bx, by, bz. And then the way I do it is I put these two rows over here, I hat. This is ax, bx, j hat. This is b. This is what? Ay, by, y, by. Okay? And then you make these little things here. And then, let's see, I get this one, and this one. Yeah. Okay? So you have AYBZ minus AZBY. This is AYBZ minus AZBY. And you'd get the same thing from multiplying this all out times I hat. If I'm going this way, it's positive. If I'm going this way, it's negative. Okay? Plus, now I'll do the j hat. AZBX minus AXBZ. AZBX minus AXBZ. And that's j hat. Plus, write this one here, k hat. AXBY minus AYBX. AXBY minus AYBX. And that's k hat. That's two vectors crossed in component form. Okay? When you take Calc 3, you should do some of this stuff. Okay? All right, you're calculating the determinant here if you've done matrices and determinants and so forth. Okay. Lots of things in physics. You need the cross product. You've got vector products for magnetic fields and other things. Okay, so torques. A torque is R cross F. So that's it in component form. We did it. I did it. You watched. Okay. Once you do this enough, you see this term has no dependence on x. You see what I mean? This is AYBZ, AZBY. No x dependence. This term has no y dependence. Okay. This term has no z dependence.